Today in our session, we're going to be talking about Amaron Aurora, take a look under the hood, and see how we provide performance and availability. So if you're not familiar with Aurora, what we're trying to provide here is a MySQL compatible relational database with full ACID capabilities that gives you the performance and availability of commercial databases at the simplicity and cost effectiveness of open source. Team's been working hard for quite a while now. We announced it at reInvent last year, for those of you who are here, and we went into production usage about 10 weeks ago, and have gotten good uptake. It's already, as Andy mentioned earlier today, AWS's fastest growing service in the time since launch. So. And today, if you happen to be deploying instances in our Tokyo region, it's available there as of today. And we'll be adding more regions as time progresses over the coming year. So here's a slide that we showed last year, slightly updated to give slightly better numbers since we've been working. And so one of the key things from a performance perspective is that we say that we can provide 100,000 write operations per second, 500,000 read operations per second. We're doing a little bit above that in this screenshot. And this is using the MySQL sysbench benchmark, which is sort of the standard in this space. And that's on an R3 8XL with 32 cores and 244 gigabytes of RAM. So you can reproduce this yourself, right? You can just provision an instance and try it out. Some folks have been doing that. We actually have a white paper that you can use to duplicate these results. And it shows some of the things that you should be doing if you want to get high performance. So for example, you want to run multiple client machines. You want to set enhanced networking on them. You actually need to tune your Linux settings a little bit in order to get the throughput you need. And then you obviously want to run in the same AZ as in terms of the clients and the servers just to get the full throughput. You should be able to get numbers very similar to the ones I showed up there. Performance is obviously lower as the instance types go down, but as you'd expect. But the fact is, benchmarks don't really matter, right? I mean, if only any of you were able to see the values in your applications running real-world workloads that the various database vendors show you in their benchmark things, life would be pretty good. We wouldn't actually be in this meeting and looking for a new database. So there are a bunch of real-world distortions that happen that are different between the benchmarks we all talk about as database vendors and what you guys deal with in the real world. So for example, requests contend with each other, right? Metadata rarely fits in the data dictionary cache, so you have to go out to disk. Data pretty much never fits entirely in RAM. You have to go out to disk there as well. And production databases need to run HA, right? You aren't going to run something on a single node, and HA takes overhead. HA, high availability. So what I'm going to show you over the next few slides is how we're doing with respect to some of these criteria relative to traditional MySQL 5.6. So here we're looking at user connection scaling going up from 50 to 5,000 using Aurora, as you'd expect. We're seeing increased throughput because Aurora is really very much about trying to generate far higher throughput. This is using the OLTP benchmark of workload from Sysbench, which has a fair bit of contention baked in with 250 tables. And if you look at RDS MySQL with 30,000 PIOPS, which is about as big a box as I can put together, it costs some money to get 30K PIOPS. And you can see that even despite all of that available capacity, you start to decline. And that really has to do with the issues within lock sharding and how the threading model works inside MySQL. And in this case, our best number is about 8 times faster as the numbers go up. Let's look at table scaling when you no longer fit into cache. So as you go from 10 tables up to 10,000 tables, we definitely start seeing a little bit of a penalty in Aurora, going from a peak of 64,000 requests per second on a write-only workload with only 1,000 connections, down to 54K. But if you look at MySQL, it's actually doing considerably worse, about 5 times worse as you go from 10 tables out to 10,000 tables. And what's interesting, and I wanted to call out here, is that this doesn't have anything to do with I/O. And the numbers, whether you're looking at local SSD, or you're looking at a RAM disk, or you're looking at a fully provisioned PIOps instance, are really all about the same, right? And I think that's a testament to all the work that the EBS team has done to ensure that they're operating at pretty high throughput compared to local disk. But it also shows contention points that are going on in the database tier. Let's take a look at data that isn't fitting in cache. So here we're scaling a database size up from 1 gigabyte, which certainly fits in pretty much anybody's cache, up to a terabyte. And you can see that Aurora is basically running about the same performance as long as we're fitting in cache, and then it drops down, as you'd expect, once you no longer fit in cache by about 4x. Whereas what's interesting with MySQL is that it actually starts declining well ahead of that point, while data is still fully cached. And in this case, if you go out to these, 100 gig, we're running 67 times faster, which is a crazy number, right? And in fact, it was so crazy for me, I told my team, like, look, you guys have obviously learned how to optimize sysbench write-only workload. Let's go run something else. And so they went out and ran Cloud Harmony's TPCC-like bench workload, which is very similar to what the TPC console runs and what numbers you can get from other things. And here it's running 136 times faster when it doesn't fit in memory anymore. And these are, on the right-hand side is transactions, on the left-hand side is statements, because those are the standard metrics for these two benchmarks for your comparison purposes. If you want to run HA or high-throughput read queries, you're probably running read replicas. And read replicas in MySQL start to degrade as you throw a lot of updates per second through the system. We can talk about how. Why that's the case. In Aurora, we actually use the read replicas as failover targets, so the replicas also provide you with HA failover capabilities. And you can see that going from 1,000 updates per second up to about 10,000, we're relatively stable at about 5 milliseconds of replica lag. Whereas MySQL is going from a few milliseconds out to over 300 seconds. We actually didn't go higher on that because it just went basically infinitely bad at that point. So for the bulk of this talk, what I really want to talk about is how, right? Because we can talk about numbers all you want, but unless you build confidence in what we're doing and how we're approaching it, it's fairly difficult to transition the database, right? And so the core of this really comes down to like improving your algorithms, sharding your locks, removing contention. So let's say you do all of that, and really anybody can go do all of that. But that's not architectural work. Once you're done with that, you're to the point where you're hitting I/O, right? Databases, well-designed databases are all about I/O. Once you do network-attached storage, it's all about packets per second. You can run about somewhere between 1 and 2 million packets per second on high-end hardware like EC2 enhanced networking, and but that's still a pretty constrained number. And the other thing that's pretty important is that if you're trying to operate at high throughput, you can't afford system calls, you can't afford context switches. So a lot of our things work in this that is architectural is about doing fewer IOs, minimizing network packets, and moving towards processing asynchronously. Let's compare and contrast. So here's IO traffic in RDS MySQL with a standby instance. So you issue a write, it goes to EBS. EBS is going to issue it to a mirror asynchronously in parallel. Then we act back once both writes have happened. Then we synchronously are going to go over to another AZ to go and issue that write using DRBD. That's the technology we use underneath our multi-AZ tech. Then you go to the standby. It has to issue the write. It propagates and comes back, and then that acts back again. And so the interesting things I'll point out here is that steps 1, 3, and 5 are sequential, and they're synchronous. And what that does is that if there's any network weather going on or instance weather going on, it's going to amplify both the latency and the jitter, right? Minimally, you're going to be looking at 3x and possibly much more than that. And the other thing that you see in this slide is that there's a lot of different types of write operations, right? There's log, there's bin log, there's data, there's a double write to avoid the fact that you're doing a destructive write and you can't afford a torn write. Does that make sense? And then there's also, of course, the FRM files for metadata. And the thing that's particularly difficult in this is that the data blocks are a good deal larger than the log, right? It's about 40x. And so you're writing those twice, so that's 80x. So that's a big deal. So, but of course, like any solid database, MySQL is going to be doing a lot of batching under the covers and so forth to try to mitigate that overhead. So what we did here is that we took the single AZ instance and did a 100 gigabit data set and ran a 30-minute sysbench write-only workload. And over that time, we're able to run about 780K transactions. And over that, we are doing a little over 7.4 million IOs for those million transactions. And that's pretty good. That's actually the work that the primary instance is seeing, just step one. So, step 2, 3, 4, 5 is not included in that 7.4 million, because really you want to focus on what the network throughput that you're going to see out of that one instance and what MySQL is seeing. All the rest of that work is our work behind the scenes. And so that's averaging 7.4 IOs per transaction, right? Let's compare it to Aurora. So in Aurora, what we're doing is that we're only shipping log records. And so what the operations that exist is that we see a bunch of log records come to us. We boxcar them together to generate a workload that's worth shipping over. We actually are segmenting the database volume across many segments, across many disks, across many storage nodes. It's something close to the world's biggest storage area network. And so we have to do a shuffle to get them over there. And then finally, we have to go and say, like, okay, how do we generate enough traffic to go out to that an individual storage node? So it's fairly complex. There's a lot of work going on behind the scenes. Interestingly here, we're only writing log records, as I mentioned. All of the steps are asynchronous. There are no data block writes. So for example, it's very typical in a database to do a checkpoint of your data every 5 minutes or so to ensure that crash recovery is contained. And it's also, of course, necessary that if you're doing a replacement of your cache, such that I have to bring a block in, if the block I'm replacing is dirty, I have to write it out. And so we don't have to do any of that either. And so we do see an amplification because we're doing 6 writes just to get sufficient durability. So there's 6 times more log writes, but 9 times less network traffic because it's only the log that's going across. And the good news is that since it's a quorum-based model where we only require 4 out of those 6 writes to come back, we actually are much more tolerant of network and storage node jitter, as well as disruptions of service, whether nodes go down or AZs go down or whatever. And so netting it out, what that means is that over that same 30 minutes, we're running 27 million transactions, which is 35 times more than the prior slide. And we're running just under 1 million IOs per million transactions per second, including that 6x amplification. And so that's 7.7 times less. And so a good deal less. And so that kind of starts to show why we're running better. It's basically we're doing less work, so it takes less time, right? Simple as that. So where did all those IOs go? I mean, they didn't just disappear, right? And so what's happening is that on the back end, what Aurora is doing is that it took that basic large monolithic database engine and it pushed that bottom quarter of it, where it's doing log processing and so on and storage, out into a multi-tenant scale-out log structured storage node system. And so we'll get a set of, a boxcar of log records at the storage node. We take them, we add them to an in-memory queue. We go and add it, persist those into an update queue and act back. So once it's persistent, we can act, right? That's the latency sensitive time. Then everything else in this process is going to be asynchronous. So we then reorganize that, sorting, grouping, et cetera, because things can show up out of order and so forth, so we have to figure all of that out. At some point, you have to say, like, okay, well, maybe I missed an I/O or two along the way because network weather or whatever. And so we have a peer-to-peer gossip protocol in the background so that the individual storage nodes can talk to each other, find out which one is missing what writes, and fill in the holes, right? And so then after that step, we basically can start to coalesce these log records into data blocks. And that's an interesting thing. So the big negative around log structured storage systems in the past was log amplification, write amplification. Because what you do is you'd write a log record, and then sometime later you have to go and coalesce those together, and then sometime later you have to go and remove, garbage collect all these things, right? And so that didn't really work out too well, even though you got this nice linear sequential pattern, as you'd like to have from a logging perspective. The nice thing in Aurora is that we're leveraging that coalesce to do exactly what the database would have done in terms of applying log records to generate data blocks. That's pretty cool. And then once we have the data blocks and the hot log set up, we can go and push it out to S3. Pushing out to S3 is continuous, it's automatic, it's incremental, and we're always doing it. So we really don't consider our data to be fully durable until it's in S3, which is 11 nines of durability. That's a lot. And then at that point, once it's in S3, we can start to garbage collect old versions. And then we're also continuously in the background scrubbing the disk. So we go and read each data block, we go and compare it to its CRC, cyclic redundancy check, and then we check for corruption, because just because you wrote it correctly doesn't mean it stays correct, right? Disk storage decays. And so that's the basic approach that we're taking on the storage node. And so let's look at the differences here. So every single step here is asynchronous. And more importantly, only the first two steps are inside the foreground latency path, right? Which consists of one write of a log record. And the input queue that's coming into any individual storage node is seeing just under 50 times less traffic than a storage node that's just acting as a dumb disk, because all it's seeing is log records, right? This is the unamplified view, because the storage nodes there's 6x of them across any given write, but any given storage node is only seeing one write. And we all obviously favor the latency sensitive operation of getting that redo record out to disk and coming and acting back. That's latency sensitive. All these other operations, they can run really whenever we have time. And we have a lot of buffering available here because it's all happening on disk. And so trading off latency for disk space is a trade any of us would make any day of the week, right? And so, all workloads end up with spikes, right? Particularly multi-tenant storage systems. You're going to see, times that it's high, times that it's low. So that gives a lot of places for us to go and do this background processing. So that's the basic storage node view of the world. Running asynchronously also gives us some other benefits. Let's look at commits. So obviously, I can't ack something back to the end user until the entire transaction, redo records, everything has been committed to disk, right? So the traditional approach to that is that you maintain a buffer of log records to write out to disk. We discovered maybe 40 years ago that you can't actually do an I/O per commit. Instead, what we have to do is do a group commit. And so you basically issue a write when the buffer is full, or you time out saying like, enough time has passed, I'd better go and send this out. But what that means is that the first writer suffers, right? He gets a latency penalty, because if enough work didn't come in, he's going to have to go and he just is waiting for no good reason. So let's compare that to Aurora. What we are able to do, because we're not just writing out to Linux, but we're writing to our own code base, going out to its own network. We're basically managing all of that in user space. We start the I/O request with the first write. And then we basically continue filling that buffer until another background thread picks up that write and sends it off to our storage nodes. And so that means that there's no first write penalty. And the individual write is marked as durable once we see 4 out of those 6 storage nodes ack it back, right? We don't have to wait for any outliers. And then once we say that we've filled in, we've seen all of the writes complete up to some particular point in time. In this slide, it's LSN 47, that LSN for log sequence number. What we can say is that, okay, so who all is waiting for LSN 47, who had tried to do a commit at some number less than LSN 47, and we act back to all of them. And that's the point where we advance the database volume durable point. And so it's basically, from the external world's perspective, it's still, of course, synchronous. From an internal perspective, it's fully asynchronous. And that just means that people can operate more quickly. In part, because of that, we also rewrote the threading pool inside MySQL. If you know standard MySQL, there's 1 thread per connection. It really limits you in terms of how many connections you can support. And it simply doesn't scale with the connection count. I mean, you can run a lot of threads, it's just memory in some sense, but what you end up with is a ton of context switches. And each context switch takes a fair amount of time to process. So MySQL Enterprise Edition actually addresses this to a degree, where they introduce this concept of thread pool with thread groups, and they basically statically allocate connections, user connections, to thread groups, and they try to run 1 connection per thread group. And if they find out that somebody is taking too long, then they'll allocate another thread and issue it as well. And what you end up with is that there's this thing called a stall threshold, where it'll go and say, well, go and figure out when you decide that something is taking too long. And and that's the point where you have to, if you set it too low, then you end up with lots of threads. If you set it too high, then you're just wasting time, because somebody might have gone out to lunch, leaving a transaction open with some locks. They might be running some long operation. Life can get hard, right? So what we've done is we implemented a different thread pool model. We have epoll at the front. All of the threads listen on top of epoll. And then we have a latch-free task queue on the back end, where we have a bunch of threads listening there if they're not already doing work. We dynamically size it. So if there aren't enough threads ready to take on work, because let's say all of them are sitting waiting for some lock, you actually have to add a thread, because the guy who's going to go and do the commit that releases all of those, you aren't going to be able to find him unless you have a thread waiting to set up, to hear the epoll. So we dynamically size up and down. So it deals with weather in your application, where like you have spikes there and so forth. And we're able to gracefully handle well over 5,000 concurrent client sessions. An interesting aspect of this is that we're able to make the threading model asynchronous for commits, because what we're able to do is that in my prior slide I talked about how we can asynchronously decide which threads are ready for a commit. So I can go and say, I can free up a thread to do useful work if all it were doing was waiting for a commit, and say that when it's advanced, let me just keep a thread available to go and act those commits back to other people. And so you remove that latency. So at this point, the latency that exists, and that's the still synchronous latency, is either you're waiting for a lock, a user operation, or you have to wait for a read I/O off of the disk. And so those are things that we're actually working on to try to eventually make those also asynchronous. Let's look at I/O traffic. So that's the last point of comparison, really, in how the system works. So if you look at traditional MySQL, what we do is we ship SQL statements off to the replica, right? What's unfortunate about that is that means that each replica is seeing the same write load as the master instance. And so, even though you're adding capacity to do reads, if you're doing 70% write workload on the master node, you're only going to get 30% read workload available to you on any of your replica instances. So that's pretty unfortunate, right? And then, of course, your data storage is duplicated and all that. The other thing that is problematic is that since these are SQL statements, you can actually end up with drift. So where it's, there's a lot of good stuff about logical data replication, but you aren't guaranteeing that what happens on one side is the same as what's happening on the other. You can guarantee it if you're running in fully synchronous, mode with, full serializability, but none of us do that. It just is too expensive on the master node. And the other thing that you'll find is that you actually need to go, rather than statement level replication, to row level replication to deal with things like phantoms and so forth. And that's also pretty difficult because it greatly expands the number of bin log operations that need to be generated and the SQL statements that need to be applied on the replica. It turns into a lot more than our running at the master node, in fact. And so, again, difficult. And of course, the storage is, a good deal more expensive. So what we do instead is that we run the replica on the same underlying storage as the master node. So, and it's multi-AZ storage, so you can run on any AZ inside that same region. Just like we send redo records to the storage nodes, we send those same redo records to the read replica. And the read replica either is responsible for basically saying, hey, do I have this data block in cache? If so, let me go and apply this change. If not, I can just throw it away because I can get that data off of the shared storage. And we also maintain this read view concept. If you're familiar with MySQL, it has this notion of what's a consistency point that I'm allowed to read from. And so we can basically advance that when we know that we've seen every commit. Because again, just like our underlying storage, we're getting these requests out of order. And so we basically need to say, when can I apply them? And when can I say that, okay, this is a point when I can advance when I'm allowed to look at the next value so that I'm in the same consistent point as the master node. And what that basically has done is it gives us, single-digit millisecond read replica lag. And the even cooler thing is that if the replica fails and comes back up, or if the master node fails and I need to promote the read replica, I actually don't lose any of the committed requests because they're all sitting there in the underlying storage. So we've been fairly busy over the last few months. Performance is an important part of the Aurora value proposition. So here's a bunch of things that we've been working on. I think the things that are in gray are things that are going to release in the next week or over the course of this month in our next couple of patches. So we've been working pretty hard. I think the thing that we're really excited about is that we're now getting customer feedback on areas where we haven't provided the same performance benefit. So for example, in the read-ahead case, we're actually running a little bit slower than MySQL because underneath the covers, the Linux system was, in the MySQL case, was actually doing read-ahead on its behalf. And we didn't get that advantage. We hadn't written that code. And so now we've implemented something similar. We're running a couple of times faster on the read-ahead case. And so those are all things where we just really welcome the feedback. You can contact any of us anytime at aurora-pm@amazon.com. And databases have an absolutely vast surface area, so we are looking for your input on where we need to improve. So with that, let me cut over to availability, because after all, performance only matters if your database is up, right? keep reminding my team of that all the time. So we do a lot of stuff here. So we've talked a little bit about how we use a quorum system for reads and writes, which makes it latency tolerant. More importantly, it means that we can drop a node, we can lose a disk, and that's fine, because it'll still run. You can lose an AZ, and it'll still run. And that's true both if it's a durability loss or it's just an intermittent blip. We do a gossip protocol to fill in the holes in replication in case we lose writes or there's some network weather that is causing us issues. We continuously back up to S3, and that doesn't have a latency penalty with it the way it would if you were taking a snapshot, right? It's something that's just part of the basic system. It's always doing that underneath the covers. The numbers we gave for 100K, 500K, or include all of that. We continuously scrub the data blocks so that you know that if you got 6 copies laid down on disk, you keep 6 copies laid down on disk. And then some of the so those are things that any real enterprise storage system is going to provide you if you go and buy a box from NetApp or EMC. What becomes useful here is that this is part of a service offering, right? So that means that we have a continuous monitoring going on in the control plane, unlike you guys where you have to monitor things yourselves. And so we can automate the process of detecting bad nodes, detecting bad disks. We can replace them from other things in the fleet rather than you're having to go and procure new capacity. And we'll just replace it and we'll repair it. Now, part of the key proposition here is I talked about how segments, we broke up the volume into many small segments. So we break up at a unit of around 10 gigabytes of logical space. And the reason we do that is that if you lose one of these segments, it doesn't take that long to repair itself, right? It's a 10 gig network on the backplane. So you can do the math on how long it takes to go and repair a 10 gigabyte segment that's gone bad. And what's neat about that is that if I actually end up with a storage node or a disk that's getting localized hotspots on it because multiple customers have landed on it and it's hot, I can actually just kill one of those segments because it doesn't take that long to move it somewhere else. And so it's helpful to us both from the perspective of hotspot management, and it's helpful just from a durability perspective, from the perspective of repairing things, because basically I need to lose, in order to lose my 4 out of 6 quorum, I need to get 3 separate failures over the time it takes me to repair one, right? And so that's a pretty unfortunate day if that happens. And another neat thing here is that if you like me geek out on quorum membership, distributed algorithms, the standard approach to that actually would force a write to stall. And so one of the things that we invested a lot into is the notion of making quorum membership changes something that is entirely transparent. So you can keep issuing writes even as underneath the covers you add nodes into your quorum, remove nodes from your quorum, and so forth. And I can answer questions on that if you're interested. So that's all at basic storage node processing kind of stuff. Let's look at that from a database user's perspective. So in the database, the traditional approach to crash recovery, since databases go down, is that you basically bring the database back up, you find out what the point you were last checkpointed, and you replay all of the logs from that point forward. And there's a famous paper called the 5-minute rule by Gray and others, where they estimated that it should be about 5 minutes between checkpoints, because that's basically a trade-off between the amount of memory you can afford and disk latency and IOPS and so forth. And that's actually stayed true for, I think, 30 years since they actually initially issued that paper. And so the problem with this operation in MySQL in particular is that the crash recovery redo application is single-threaded. And so since it's single-threaded, you may end up with 32 cores generating forward traffic over 5 minutes over a checkpoint, but one core applying the change log, the redo log onto the blocks after you come up. The other problem is that you're going to be doing IOs here, whereas when you're doing the foreground traffic, it may have been against blocks in your buffer cache. Whereas now you have to go and warm up your cache and get these things off of disk, and that also adds time. And if they're going across a multitude of tables inside a data dictionary, you have to page those in as well. And so, there's nothing that guarantees that it's going to be 5 minutes. It probably is going to be 5 minutes or less. It might be as low as a few seconds. It might be I've seen it go as long as an hour. I mean, that's obviously a crazy outlier case, but that's not what you want to see because it's not what you manage to, right? If you look at Amaron Aurora, what we've done is we've built a log-structured storage system underneath the covers. Each 10 gigabyte segment has its own segmented portion of the redo log. If you ask for a data block out of Aurora storage, it basically goes and tries to get a data block. It checks to see if any log records have been issued since that point based on the read view you're asking for, and it'll go and say, well, let me go apply those before I give it to you, right? And so what's neat about that is that the same process that is happening for foreground processing is happening for recovery, which is really important if you're building a recovery system that it's not dusty code that goes bad. And the other thing that's really important is that this is an operation that's parallel, distributed, asynchronous, and yet more importantly, you don't have to do it at startup time. I can just start up. And it's really only at the, because if you issue an IO, it's going to do the same thing that it would have done if it was happening in the normal course of behavior. It's going to go and apply the records it needs just for that data block in order to return it to you. So that's nice, there's none of this 5-minute stuff. The other thing that we did in Aurora to sort of assist with this is that we moved the buffer cache out of the database process. And that might sound esoteric, but what it ends up meaning is that the cache stays warm if you have to restart the database. So for example, let's say you ran into an application deadlock and you need to bounce things in order to come back up. Now, we have, if you, are a DevOps guy like me, you have run into these cases where you use relational databases under the covers, and it's hard to say how long it's going to be until that cache is warm again. And what you end up doing is you send a trickle load through the system, because if you go and put the full load against it, you end up, having so much IOs going to the back end that the thing goes belly up again. And so that's, it's a bad time. So in this case, since the cache is already warm, you can resume fully loaded operations much, much faster. And you don't have to think about when that is, it just happens. And so the combination of survivable caches and instant crash recovery makes database failures pretty fast. Let's look at what the timeline would look like. So in traditional MySQL, what you'd be doing is you get a database failure, you have to detect it, right? So for example, in multi-AZ, we have a witness that sits there and watches the database, runs a health check against it every so often, every 5 seconds. And once it gets like multiple blips, it says, okay, I've declared this node bad, I'm gonna cut it over. Then you bring up the new standby instance, you start running recovery. Could take arbitrarily long. Hopefully not too long, but could take long. And then you also have to have your DNS cutovers to move the IP from primary to secondary. That can also take a little while. So with Aurora, the failure detection, we're able to compress it quite a bit to 15 to 20 seconds right now, because the cost of making a mistake isn't large. You can bring up a new system pretty quickly. You don't lose any commits, and it's basically a short blip. The recovery is somewhere between 3 and 20 seconds. That's basically right now it depends on instance size, because we have to go and look through all of the buffer cache to figure out whether we need to throw away blocks that are in the past of what some of the updates might be. And so that takes longer on a big instance than a small instance. But right now it's somewhere between, it's 3 instances on an R3 large, it's somewhere around 20 on an R3 8XL, and then your app's running. So wait a second, I didn't talk about DNS propagation there. And so the DNS, of course, does need to propagate, but we've been working with MariaDB on their drivers, their JDBC, ODBC drivers. And MariaDB's drivers already support MySQL, Percona, and of course MariaDB. They also added support for Aurora. And one of the things and so that's kind of nice because, changing your database engine, it's painful. Changing every place that you need to change ODBC or JDBC driver, that's really painful, right? And so the fact that we have something that works across the full range, I think that's nice. Even, and it's not ours, but I think, we're really supportive of them, their work there. One of the things they did on our behalf is that they look at a system table, they look at all of the read replicas that are available, they figure out what the physical IP addresses are, and that way they can do a cutover by just polling which other guys respond back that they're the master if they lose connectivity to what was previously the master. And so they can get to the guy who is now the new declared master without having to do DNS propagation. So I mean, DNS propagation will still happen and so forth, but you can get the failover in a nice contained time, whereas DNS propagation can take a fairly long time depending on where you are and the network topology and all of this other stuff, right? It's hard to estimate that, and we really want to have controlled environments. And I really kind of hope that next year, if I'm doing this slide, the numbers are about half this size, because I think there's about that much fat left in it. One of the things we talk about is that it's one thing for me to go and claim that we can do all of this stuff, but we really need to prove it, and it's hard to prove this stuff in managed systems and environments like ours. So one of the things that we allow you to do is certainly crash your instance or node or some of the various other components in the system. You can simulate disk failures. You can simulate the percentage. You can simulate how long they're down. You can simulate network weather, either total or partial, and so forth. And that just lets you go and validate that this stuff works for your own needs. With that, here's a quick look at the Aurora team that actually builds this stuff, whereas I just talk about it. And thanks to them for all this work. And with that, I can jump forward to questions, if you have any. Yeah. So the question was, what's involved in moving a production RDS MySQL instance to Aurora? So we've tried really hard to make that simple. We'll actually be talking about that in the intro to Aurora session tomorrow and walking you through it. But it's basically a handful of console clicks where you have your RDS MySQL instance, and you can basically just tell it to migrate to Aurora. And underneath the covers, what we do is that, of course, the underlying storage is different. So we read all of the blocks, and we write them all in our own format. And that's basically it. It basically runs at line rate speed. If some of you guys tried that in our preview, over the course of preview, it's somewhere between 5 and 10 times faster. We fixed some stuff. So right now it's running closer to line rate than before. So it should be simple. So the question was, is there downtime? So one of the things you could choose to do is move a replica over, right? Something like that. Disconnect it and then connect connect it back up, because I kind of talked about how there are issues with bin log replication, but we still support bin log replication, and so we can act as a source, we can act as a target, all of that stuff works, and so you can do all of the standard things that you do for moving from one MySQL to another in the same way. Okay. And then, of course, we announced earlier today a database migration service. So if you chose to, you could also use that. Yes, sir. I'm sorry, could you repeat that? So the question was, are there any plans for multi-region Aurora? So I will say that the two requests I hear all the time, most often, is one is, hey, could you do an Aurora for Postgres? And could you do multi-master, multi-region Aurora? And so, those are obviously both heavy lift projects. Those were things that would be pretty challenging for us to take on until we went production. We're taking a hard look. So, there's nothing I can talk about now, but that's because, we're taking a hard look at those sorts of things. Yes, sir. So the question was, in other RDS databases, there's a failover event that happens when you have to upgrade an instance. Are we able to eliminate that for Aurora? So partially. We're able to eliminate that for the storage tier because we basically upgrade AZ at a time. So in some sense, one of the benefits of that is that we're continuously testing our 4 out of 6 protocol because we're basically introducing failures in some sense all the time. We have not managed to fix that yet for the database engine itself. So you do have a failover and then a failback with all of the sort of situational work that we talked about there. So the question was, are we able to refine it in any way to reduce the failure detection time and so on? So yes, it should be quite a bit shorter for all of the reasons I talked about earlier. Sorry, go ahead.
Is there a reason to not choose Aurora if you want
So the question is, okay, so you've talked up Aurora quite a bit. Why not use it? And so, there are a handful of reasons. So one is that when we say we're compatible with MySQL, what we mean is MySQL 5.6 using InnoDB. And so if you're using one of the other engines, ISAM or something like that, you will have to undergo some work in order to transition, or one of the multitude of other storage engines that's out there. If you're using 5.5 or God forbid 5.1, you have to think about it's not going to really work for you, right? And so forth. If you're doing a dev test instance, then you might be wanting to run on a micro, and Aurora only goes down to an R3.large, so it might be effective for you to run on a micro or a small for you're doing your dev. But since we're compatible, it's very possible for you to sort of make, as part of your code pipeline, a promotion up to Aurora for your GA usage. Yes, sir. The question was, is there an announced plan for encryption at rest? So that it should be in 3 weeks with KMS keys. I'm sorry, could you repeat that? Uh-huh. Got it. So the question was, in my discussion, I compared MySQL on Linux to Aurora a few times. Does that mean that Aurora is not on Linux? No, that was not my intention. Aurora is on Linux. The difference is that if you're running EBS, it basically is running underneath the covers as underneath Linux, inside DOM0 in order to do the movement. And so you're issuing an I/O transparently as though it's a disk. It goes through the DOM-U kernel and then into the DOM0 kernel in order to run the movement over into network-attached storage using EBS. In the case of Aurora, we're not going through that layer of processing. right? Because all we're doing inside user space, we're saying that, hey, I need to issue a request out to my storage nodes, right? So, I mean, that's a different system call, obviously, but it's a network system call, not an I/O system call. And so that means that the code path down at that layer is quite different. Yeah. The question was, can I create an Aurora instance through a CloudFormation template? I believe the answer to that is that not yet, but they're working on it. I could be mistaken. I know that they announced something a little bit ago, but I'm a little bit confused about it. I'm sorry, they fixed it last week. Thank you. Yeah. So the question was, can you support, are there any plans to support smaller instance sizes for Aurora? That is something I hear a lot, and there is a trade-off that's going on with Aurora where we're introducing extra load in the system to do all the shuffling and so forth, and so we do benefit from space. And definitely, as you go down to even the R3.large, you're not necessarily seeing meaningful performance gains. You know, you will if you go and do the disk type traffic. You're not going to see it using memory resident workloads. You will, of course, get all of the benefits of durability and availability and crash recovery times. So we can go down smaller, but we're going to have to work on shrinking down some of the things we're doing that help us when we're going to very large instance sizes. And so, you know, it's a request we hear all the time. It's something we think about. It might be a moderate-sized lift for us to accomplish. And I would encourage people doing that to be thinking about that from a dev test perspective versus you know, sort of a production workload perspective, right? Because it's kind of odd to be running 6 copies, 3 AZ storage, using SSDs as a backplane and running a micro, right? So that, you know, it's just, you know. Are there any other questions here? Yes, sir. I'm sorry, I couldn't hear you.
Are there any plans to support a read-only cluster?
The question was, are there any plans to support a read-only cluster endpoint? Yes. We aren't that far along on it, but you can imagine that you know, in the same way that we can detect from a driver all of the failover targets and detect which are the failover things, you could also go and think about the work necessary to say, like, which of my read replicas is warmest, or, you know, and which one should I go and route to, and go and actually figure out automatically whether you're inside a write transaction, and you know, you can move or not, or so on. So yeah, that would make a lot of sense. We're interested in supporting that, and particularly if you're starting to run something like up to 15 read replicas the way we support, I think that that's a useful thing. So it doesn't exist today, of course. So the question was, when will Aurora be available under BAA? So we're working on that. Clearly, getting encryption done is a precursor. So I think after that, we can start working on the process through, you know, HIPAA and all the rest of it. And you know, that's primarily a matter of going through, you know, a meeting a week for, you know, as long as it takes. But you know, it's a somewhat lengthy process, but it's important to us. Anything else? Oh, yes, back in the back. The question was, any plans to support Aurora in California? And so we want to expand Aurora to every region as soon as we have 3 AZs available there. So Aurora requires 3 AZ storage. It's a fundamental design point for us. It's actually fairly complex for us to be able to try to move to support both a 2AZ architecture and a 3AZ architecture. In particular, if you think about 6 copies and 2 AZs, if the AZ goes down, you've lost 3 copies. It's hard to define a quorum model that makes sense. So we definitely are looking at that inside you know, the AWS team as a whole. You know, there are other things that require 3AZ storage, and So, it's something that we're taking a hard look at. Is California critical for you guys? Okay, got it. Thank you. I'm sorry, could you say that again? Are there any plans to support MySQL backup and restore on Aurora? I probably will want to talk to you after the session finishes to understand that in a little bit more depth. I think the direction I've been taking to date is to basically do physical backups underneath the covers, which are segmented, and there's a lot of complications when you do that about being able to assemble together what the backups look like. But I would assume that you're looking at that from a transportability from location to location, and we'll just want to understand whether the backup model is the better model for that, or is some of our products like data migration service better. But let me just talk to you in detail to understand your requirements there. Sorry, go ahead. So the question was, will there be anything akin to DynamoDB streams? And so I think there, to a degree, Binlog is sort of that solution today. There are issues with bin logs, positive and negative. I mean, logical replication is kind of a good thing. One of the things that we are doing in the very short term is that using Aurora as a data migration service point. And so you can certainly use change data capture out of data migration service and go from source to target even within the AWS cloud. And that's one way that you can certainly connect these things together. It might make sense to do what you're requesting. I'd probably want to just understand that in some detail. Yes, ma'am. I'm sorry. So the question was, are there any changes in deadlocking, or is it still like it was in MySQL? So we completely rewrote the lock manager. So, there was a slide that someone wanted to put in my presentation, and I took it out because it would have taken like 2 hours to go through it. And so, we can talk about the new approach, so it's going to be different, but I'll probably need to understand in detail the underlying question that, because there's clearly some pain that you're encountering today that we'll want to see whether we've addressed it. Does Aurora point-in-time restore support what? Temp tables. Yes. So support temp tables was the question. So one of the interesting things with Aurora is that since we're only shipping log records, that basically means we have to make everything a log record. So a lot of the things like FRM files, like bin logs, like temp tables, actually need to move into things that are managed inside the database so that they can have the same durability as everything else, right? And so one of the nice side effects of that is that everything is actually at the same point in time. And so one of the challenges I believe MySQL has is that you can do a point-in-time restore, but it actually gets kind of complicated to align the FRM files with the InnoDB files because there isn't really consistency from a log point of view. Whereas by storing everything inside the database itself, we can guarantee that there's a consistency point that is a log record, and both the metadata and the data and all the rest of it is aligned with that point. Did that make sense? Yes, sir. So the question was, is there any performance difference between single table or file per table space and all of that? No. So, we do obviously support file per table now. That was actually something that we learned out of the preview process because initially we hadn't supported that, but then it turned out to be the default and super popular with people, and there are also some other things that just required it. like row size, which was kind of a strange linkage between those two concepts. But so we just net had to support it. But underneath the covers, it doesn't really mean anything to us because things are spread widely without really any consideration about table space per se. Yes, ma'am. In MySQL 5.7, did you say? Or? So the question was, are we going to add common table expressions and so forth? So our intention is to match the surface area. So at this point, we're at a particular version, we're backporting patches, but our expectation and our intent is to stay fully compatible with the functional surface area. So as they add functionality, we'll want to add that to our product as well. Okay, last question, if any. Otherwise, we can talk outside. Yes, sir.
You talked briefly earlier about smart routing of read requests using replicas.
Uh-huh.
Does the functionality exist right now to route between a read replica for reads and then the mask of the writes?
So the question was, is there any smart routing functionality today between writes and reads and so forth? So today, no. You can actually choose to implement it yourself because the underlying information is available in system tables about where all the read replicas are and what kind of lag they're seeing and how much load they're seeing. So that helps a little bit, but certainly for the majority of us that would just like a driver to do this stuff because it should, it's not there right now. Okay, that was the last question. Thank you very much for your time.